Thank you, Brian and Mark. Good morning, everyone. I think it's still morning. So uh, I am Ali Zahir, and I'm currently working at the University of Leicester. I was part of this Base 2 project of DiRAC for the last year, and I've been doing some work in the energy consumption of the analysis workflows. So today I will be talking about this energy-aware jobs scheduling for HPC clusters. Just to give you an overview of the presentation today, I will briefly be talking about the growing challenge we are facing right now, especially in terms of energy, with a little bit of background. What is the basic workflow execution process? What are the constraints of scheduling and energy in those execution processes? What were the basic initial findings, and then which will be followed by the proposed solution, which we have proposed last year, and we are still working on that, and we'll show some results as well. So we know that all the large-scale experiments, such as ALICE at CERN or cosmological simulations at DiRAC and square kilometer array, South Africa, Australia, all these big, large experiments, they generate massive amount of data, like petabytes of data. Even at CERN, ALICE is generate like 20 petabytes per second when the collisions are happening. So we need to store that data. We need to process that data, and that requires massive compute and storage resources in the HPC environment. The reason for that is that we have got like thousands of users, researchers, physicists, scientists all over the world, which basically needs that data to perform their analysis workflows, jobs, tasks. So, and of course, if you can count the numbers, if thousands of physicists are working on that, the number of tasks could be like hundreds of thousands, or workflows. So to execute those hundreds of thousands of workflows, we need like massive computing resources. We need massive storage resources. So, and of course, they will come with the biggest challenge, which is the energy consumption. Like if the system or the HPC is running on the full capacity and it's running the those analysis workflows, it will require massive computing power, massive computing resources, and then massive energy. That energy ultimately leads to the cost, which is basically we need to pay in terms of electricity bills. Right now, we know that the electricity prices are rising day by day, and the carbon emissions, everyone is like working over, let's reduce the carbon emissions. So we thought, okay, let's talk about this thing and how we can come up with a solution through which, because normally what happens is that if we go for the performance, okay, everyone is talking about the performance. We have scheduling algorithms, we have state-of-the-art systems, which are mainly focused on the performance. But again, that performance comes with the cost of energy, the cost of electricity. So is there any way we can say that, okay, I am okay by compromising a little bit of performance, but ultimately, if it saves me like 5, 10, 15% of energy, if I am ready to compromise some of the performance. So again, to find these exact numbers, we made some work, and then I'll show you what are the results for this. So just to give an overview of what is the normal workflow execution process, we do have, like, as I say, hundreds and thousands of analysis workflows, which contains multiple tasks, jobs, whatever you want to say, which you want to run on the HPC systems. So again, there are like multiple scheduling techniques available. We have designed few techniques. I will briefly go through with the scheduling techniques which we have designed in the next slide. But again, they are mainly focused on the performance. That is, to execute those analysis workflows or jobs as quickly as possible. In our work, first, we have categorized those workflows. Like, okay, let's say in this case study, we specifically look into the ALICE analysis jobs at CERN. What are those workflows? So they have got like 5 different categories. There are many more as well, but we took like 5 of them. So like event reconstruction, particle identification, anomaly detection, and some others. And then after categorizing those workflows, we need to find an optimized scheduling technique to run those workflows so that each workflow has a different characteristics, different number of tasks, different complexity level. So if let's say so we cannot treat all of them with the same bullet. So we need to come up with a bespoke solution for every analysis workflow. Also, if the system is running on its full capacity, it's consuming maximum electricity. If we talk about any of the scheduling algorithm, it's going to consume electricity, power, and then it's going to give us some output. So just to give us the brief overview of the scheduling algorithm, we have proposed few algorithms. Locality-aware scheduling, LAS with prefetching. It's basically the locality-aware with the added features of the prefetching. And then we have proposed speculative-aware scheduling. In terms of locality-aware scheduling, it basically schedules the data on the basis of the locality of the task. For example, in Alice analysis, there are multiple tasks which requires similar kind of data set. So for normal processes that, whenever the task arrives for the execution, it has to wait for the resources. Those resources which were generated by the experiment, they are sitting in the HPC storage environment. So the system has to load that small event or the storage data from the storage element, brings it to the memory, execute it, and then discard it. And then the same process goes for the next task. So what happened is that memory has to load and unload data again and again. This takes time. So to reduce that thing, so we have come up with this technique that the task with or the workflow with similar data set requirements, we give them the priority so that when the task arrives, its input requirements should be present in the memory. So it doesn't have to wait. It will get the results as quickly as possible. Again, it is performance measured, but it is based on performance. We are getting the maximum performance by pushing the system. And next task we have proposed is the speculation. It speculates the task that, okay, there are some tasks which follows some pattern. So, and then it predicts the task based on the historical logs that, okay, this task follows a specific pattern. It arrives at this specific time with these requirements. So we predict that task and, okay, it's going to come in. We will bring its resources ahead of time into the system so that it doesn't have to wait. Then we get the maximum performance out of this as well. So these three, and then there are like thousands of other scheduling algorithms which are performance focused. So are these. Now, after this, what we have achieved is the maximum performance in terms of the execution time. So we are saving time right now. What are the consequences? So we are saving time at the cost of energy. So what we have done is that since we know that energy is kind of a scientific phenomena, we do have many algorithms, tools, I would say even hardware and software tools, which are in the new systems. We do have system tools which basically calculates the power consumption event by event. We can even calculate the consumption of a single script of a code. So we do come up with this technique to calculate the energy consumption of all those scheduling algorithms which we have proposed. And then at the end of it, we came, there are a few libraries, even if you want to go for like software solution, PES utils, maybe you might heard of that, the PyJols, and I think HP come up with this built-in tool as well, through which you can calculate the power consumption. So through power consumption, you can calculate the energy consumption of the process. So after this metrics, we came up with this data set which contains multiple combinations. For example, all the scheduling techniques, what are the, they're like, we have got 5 workflows in that case. So what is the optimization time of one scheduling technique along with its energy consumption? For example, there is, I think it's very small, but I think you will get the slide so you can have a look at that later. We have got LAS, locality-aware scheduler. And if the workflow 1 is using locality-aware scheduling technique, workflow 1 contains X number of tasks in it. Each task requires specific data set and it has different execution time requirements. So we came up with, there are 2 results. One is the total turnaround time of executing that task or a workflow. and along with the energy consumption of that specific workflow by using locality-aware scheduling technique. So that's how we kind of profile different scheduling techniques on the basis of their execution time, their energy consumption, power consumption, and one more thing. Right now, the system is running it on its full capacity. That means it's using 100% of the CPU resources, memory, cooling, everything. Now, how we can control the energy? We know that the CPU and the GPU, these are the most power consuming devices in our system. So what is the possibility if we can reduce the clock speed? I think many people have done that work as well. Okay, let's say we reduce the clock speed of the system. What will be the impact on the performance? Of course, it's going to go down. If we reduce it to, like, let's say, if there's a 2 gigahertz processor, it's running on 100% capacity, it's giving us the maximum performance. What if we reduce it to like 70%, 50%? Of course, we will end up saving electricity because it will be consuming less energy, but at the cost of performance, at the cost of time. So is there any way we can find the balance between these two? Okay, because there are many tasks which are not time dependent, which are not very performance oriented, which are not very keen about, okay, we need to get the results as quickly as possible. Because, and again, but I understand there are some, but most of them are not. So what if we can come up with the solution that we can say, okay, I am ready to compromise, like, let's say, few percent of the performance, but if the end, it will give me like 10% of the energy saved. If I manage to save like 15% of the energy by compromising, let's say, 10% of the time. So again, we need to find the trade-off with that. So what we have done is that this is kind of our initial results. We came up with this idea so to visualize how the system will behave if we look into different possibilities by compromising the performance, like reducing the clock speed, reducing the system configuration, as we call it as operational configuration. If we reduce the operational configuration, how the system will behave and what will be the effect of that reduction on energy consumption. So we came up with this idea to, let's say, generate more data. We do have initial results, but we say that, okay, let's visualize some more data. How? Obviously, the scope of our current experiments were limited. We cannot visualize like hundreds of thousands of possibilities because we have got many schedulers, we have got many types of workflows, we have got many scenarios. So what we have came up with this idea is that let's generate data by using autoencoders. That's the basic thing. We can generate anything from through AI, but by generating, we don't want to generate random data. So what is happening here is that we came up with this computational fluid dynamics based physics-informed variational autoencoder technique, which generates data on the basis of scientific phenomena of the energy consumption, along with the physics of computational fluid dynamics. The reason we have used CFD is we want to know how the heat is generated in the HPC systems, how it is transferring, and then how it's basically dissipating in the environment. So those equations gave us an idea that how this phenomena is happening, along with the scientific process or scientific proof of energy consumption. So we do have like equations of energy consumption. We do have the phenomena of fluid dynamics. What we have done is that we use this science and we gave that to the loss function of our variational autoencoder. We trained our autoencoder and we asked us to generate more data. At the end of it, we managed to generate loads and loads of combinations. Now, the thing is, by using those two techniques, the generated data is like very realistic, and it's not at random numbers, which has many possibilities of different scheduling algorithms, different timings, different operational configuration scenarios, and ultimately, we want to see the impact on the energy consumption. Since we were generating data, so obviously we need to do some like uncertainty quantification and error handling. So the thing is, as I said earlier, we don't want to generate such data, let's say, which maybe reduce the operational configuration to less than 50%. If we reduce the computational power of a system to less than 50%, it's going to severely impact the overall performance. We cannot afford that. And on the other hand, if it's like doing 0 to 3, 5, less than 5% of the reductions, we won't be able to see any effect on the energy. So this has to be like in a controlled environment. So we limit our system so that it only generates the data from 5% to, let's say, 25%, but it's variable. We can manage that. That's how, and then we did some uncertainty quantification, which basically, for that, we have used a bootstrap resampling technique, which is basically the statistical model which we can use for the validation of these synthetic data. And we came up with like pretty good results, like 90 to 95% of the confidence level of our generated data. So after that, we managed to generate loads and loads of data. And if we look into this, this is just a sample, which I kind of brought here. Maybe you won't be able to see, but again, we have multiple scheduling techniques, multiple workflows, different scenarios of tasks. And then we have checked the possibility of reducing the operational configuration of 20%. How the system is performing. Let's say we reduce the operational configuration to 20%. What is the impact on turnaround time, along with the impact on energy consumption and power? So if we reduce it 20%, we manage to save X amount of energy. If we reduce it to 15%, we manage to save Y amount of energy, and same goes on. So again, this gave us the complete picture of how of that, what are the possibilities we can have. And after statistical analysis, and there can be like many solutions available, once we have the visualization of the complete picture, we can see that, okay, this specific workflow or a task, if we run that on a specific configuration of a system, this will give us the optimized performance by not reducing, by not taking so much energy. So with some results, we managed to, again, it was dependent, it was a specific scenario, but again, the solution is generic. So for example, in this case, we managed to save up to like 10% energy for workflow 1, because the system told us that if you use that specific scheduling technique, which is the speculative aware scheduling, and if you tune down your system to 15%, it's going to impact the optimization time to 5%. It will increase the turnaround time up to 5%, but at the end of the day, it will save us 10% of the energy, which is, I think, a lot in most of the cases. Because if you talk about DiRAC or like if CERN or any big data center, the energy consumption, the energy bills are like in millions a month. So that if we manage to save like 10% of that million, it's still a pretty good number. So yeah, that is it, I believe. I'm not sure. I think I still have time or time here. So again, if you have questions, so we can discuss that as well. So thank you.
Thank you, Ali. Any questions? Sir.
I find it very interesting to see that combination of scheduler and clock adjustment, because we messed around with some AMD Genoa generation CPUs, and we found that just messing with the clock speed, you could actually increase the amount of kilowatt hours required by making the code run slow. So the end-to-end time and then all the other overheads of the machine would make it actually cost you more kilowatt hours, even though your peak kilowatts was lower.
I mean, it's true. Again, that's why we were looking for out of multiple combinations. It's not like a hard and fast rule to clock down to certain cycle. You can have a look at the performance optimization. Okay, if we reduce it to specific clock speed, what is the impact? So again, it is just an experimental environment right now, but we are coming up with the more generic solution, which will be, let's say, good for a specific environment. Because right now we are more focused on the workflow categorization, because what type of workflows require what sort of what sort of configurations, and we are like more focused on that. You're right. Again, that's why we're not downcycling the speed so much, because again, it's going to impact the overall performance. That's why I need to find that optimization or the trade-off between these two, that, okay, we are willing to sacrifice some of the performance, but if at the end of the day, it's give us like more energy consumption saving. So yeah.
Any other questions? No? Okay. Thank you, Alex.